Chapter 7, Introduction to Sampling Distributions. In this video, we'll learn how to calculate the mean and standard deviation for the sampling distribution of the sample proportion, p-bar. Another common measure that we often use in business statistics is the proportion. For our population, when we're trying to find the proportion, it's the fraction of values in a population that has a specific attribute. Similarly, if we wanted to know the proportion in a sample, it's also the same idea in that it's a fraction of items from the sample that have a particular attribute of interest. So we can see here in our formulas that they look very similar, but the capitalization or symbols used denote whether it's a population or a sample. So here we have little p, which means our population proportion. To find the population proportion for any particular attribute we're interested in, it is big X, or the number of items in our population that has that attribute of interest, divided by our big N, which is our population size. Similarly, with our sample proportion, if I were to pull a sample out of the entire population I was interested in, this would be denoted by P bar. And to calculate it similarly, we'll take our little x, or the number of items in our sample that has the attribute of interest, divided by our little n, or sample size. So it's important to know the difference between little p, which means population proportion, and p bar, which is our sample proportion. It's common to mix the two up, so just make note. Here are some examples of proportions. Say we wanted to know the proportion of customers who use a 20% coupon at Bed Bath & Beyond. In this example, the attribute of interest is whether or not the customers use a 20% coupon. In our second example, this is the proportion of Americans who own a home. Again, our attribute of interest is home ownership. In our third example, we have the proportion of Maricosta students who eat at the cafeteria on campus. The attribute of interest here is eating at the campus cafeteria. And our fourth example is the proportion of defective phones. In each of these, we can find the proportion of our attribute of interest by taking the number who have this particular attribute divided by our population size or our sample size, depending on if we're looking at populations or samples. Similarly, when we learned about the sampling error for mean, here is the sampling error for a proportion. Again, we will determine the population proportion, find our sample proportion, that's p bar, and then compute the sampling error by taking our sample proportion minus our population proportion. Recall that this sample always comes first in our sampling error and then is subtracted by our population. Some things to note: when we're working with the sampling distribution of p bar, the best estimate of our population proportion p will be our sample proportion, or p bar. Any inference we make about how close our estimate is to the true population value will be based on the distribution of the sample proportion p bar. So recall when we learned about distributions, this is the way our curve looks. And in this case, our distribution is binomial, because for a proportion, they either have the attribute or they don't. Recall with the binomial, we're looking at two possible outcomes. Another thing to note is the sample size as it relates to our sampling distribution for p bar. When we talked about sampling distributions for the mean, or x bar, the conservative rule of thumb was we needed a sample size of 30 or more. When we're working with proportions, to determine if our sample size is large enough, we use the following two formulas, where we take our n, our sample size, times our p, the probability of success for our outcome of interest, and that should be greater or equal to 5. And we will plug in the same n and the p in our second formula, where we'll take 1 minus p and then multiply that by our sample size, and that should be greater or equal to 5. So as long as both formulas are satisfied, then we know we can use the normal distribution to approximate the discrete binomial distribution. In other words, we can now use Appendix D to find the probability of something occurring. Here are the two formulas, our mean and standard error for our sampling distribution of our sample proportion, or our p bar. So here we see our mean for the sampling distribution. It's essentially just our P, or the population proportion. You'll be given this in any problem you see in the textbook or on an exam, for instance, or in a real-world example. And the standard error is this formula where we're going to take the square root of our population proportion times 1 minus our population proportion divided by our sample size. Earlier in the chapter, we learned several theorems that allowed us to apply the sampling distribution of the mean, or x bar. Similarly, Theorem 5 takes all the pieces that we've just discussed, and it allows us to work with the sampling distribution of p bar. So regardless of the value of the population proportion p, aside from p being 0 or 1, the sampling distribution for our sample proportion will be approximately normally distributed, with our mean and our standard error, as long as our sample sizes are sufficiently large. And note that the approximation to the normal distribution improves as the sample size increases and p approaches 0.5. Just like when we worked with the sampling distribution of the mean, we can also convert our sampling distributions of p bar into z's. So here is the formula to convert our p bar into a z. You'll take our sample proportion, or p bar, minus our population proportion, and we'll divide it by the standard error. Again, I've listed down here below the formula for our standard error. That's our population proportion multiplied by 1 minus our population proportion, divided by n, and then square root the entire thing. Let's look at an example. So a big problem for taxpayers has been the recent increase in fraudulent tax returns being filed with the IRS in the name of taxpayers. So suppose the IRS believes that 15% of all taxpayers will be affected in 2016. Assuming the true proportion of taxpayers who get hacked is 0.15, what is the probability that more than 40 in a random sample of 200 will have been hacked? In this case, our attribute of interest is people who get hacked on their tax returns. Note in this word problem, we have the population proportion provided to us twice in two different formats. Here, the population proportion is listed as 15%. How we know it's the population proportion is in the context of the story, because as we see, it says 15% of all taxpayers will be affected in 2016. So our population of interest here is taxpayers in 2016. Our population proportion is given to us again in the very next statement, assuming that the true proportion of taxpayers who get hacked is 0.15. And remember that 0.15 and 15% mean the same thing. They're just in different formats. Whenever you see in the word problem, if it's in a percentage, you'll want to convert it into decimal format in order to work with our formulas. So we have our P at 0.15, which is our population proportion, and we also need to calculate our sample proportion. So in our problem, we want to look for where's our sample. In this case, it is at the very end of our statement where we're looking for 40 in a random sample of 200, because the attribute of interest is those that get hacked. So we'll take x divided by n. Our attribute of interest is the number of people who get hacked. That's 40, and we'll divide it by our sample size of 200. So when we divide 40 by 200, we get a sample proportion, or p bar, of 0.2. In our question, when we write it as our event of interest, we're essentially saying that we want to know the probability, that's the big P, of our sample proportion, that's our p bar, will be greater than 0.2. Because recall in the statement here, it said, what is the probability that more than 40 in a random sample? But I'm not going to write 40 in my mathematical statement. I'm going to write the proportion, in this case, proportion of our 40 over 200 at 0.2. So let's look at what this looks like in a normal distribution, thanks to Theorem 5 that says we can now calculate the sampling distribution for a proportion through our various components. So if I were to draw my normal distribution, where we have our population proportion of 0.15, or 15% of all taxpayers in 2016 will get hacked, according to the IRS. And then in our sample proportion, where we took 40 divided by 200, that gave us our sample proportion of 0.2. And in our story, what we're interested in is the probability that more than 0.2 will get hacked. So there's our event of interest there. So all we've done is taken the pieces from our word problem, put it into a visual representation of our normal distribution. But thanks to Theorem 5, if I know something is normally distributed, we want to convert it into z-values and use our appendix D to find the probability of this area. So to convert our sample proportion into a z-value, we're going to use this formula here. Note we have our p-bar, or our sample proportion, minus p, which is our population proportion. In other words, this numerator right here is our sampling error. And then down in the bottom right here is our standard error formula. Note it is our population proportions and our sample size that we plug in here. So we want to make sure we get our p-bars, our sample proportions, and our p, our population proportions, in the right place. You don't want to mix the two up. So I'm going to plug in my 0.2, my sample proportion, minus my population proportion of 0.15, and I'm going to plug in my population proportion at 0.15, and 1 minus 0.15, that gives me 0.85, and divide it by our sample size of 200, and then square root it. That should give us 1.98 for our z-value. So if I add that to my curve, recall before this was 0.2, that was our sample proportion on our last slide, but I've just converted it into a z-value of 1.98, and I'm going to draw it right here. Another way of saying is we're interested in the probability that our z-value will be greater than 1.98. Now, since we know our z-value, we can go ahead and go to the standard normal table, or our appendix D. And so our appendix, when we look up 1.98, gives us the area from the middle out to the right. So this 0.4761 we see in the table tells us this area right here. Now we already learned how to read and use our appendix D in the previous chapter, that if we want this shaded area here, but I know this area thanks to our appendix D, I have to apply the rule of our curve, in that I know our entire curve is worth 1, and this half of the curve is worth 0.5. If I know this half of the curve is 0.5, and I know this area is 0.4761, I'm going to subtract 0.5 and the probability according to my appendix, and that will give us the shaded area here for when the probability that our z-value is greater than 1.98 will be 0.0239, or 2.39% chance that our probability will be greater than 1.98, or the probability that we will have more than 40 hacked tax returns out of our sample of 200. Now go ahead and pull out your worksheet if you don't have it already in front of you, and let's do another practice problem. This is number 57 from our textbook. Say that 10% of U.S. engineers, this includes electrical, mechanical, civil, and industrial, are women. Suppose a random sample of 50 engineers is selected. Part A asks, how likely is it that the sample of engineers will contain 8 or more women in these positions? So our first step is we want to determine our population proportion. What's our P? In this case, it's given to us in the story at 10% of U.S. engineers. How I know this is the population is because we're talking about the United States as a whole, U.S. engineers. So our P is 0.10, or the decimal form of 10%. In step 2, we need to calculate the sample proportion we're interested in studying. So that was given to us in part A in the question, where it asks how likely is it that the sample of 50 engineers will contain 8 or more women. So in this case, our attribute of interest is whether the engineer is a woman. So our X will be 8, and our N is our sample of 50. Thus, our sample proportion, when we take 8 divided by 50, is 0.16. In step 3, we want to define the event of interest. Again, this is given to us in part A, in that we want to know the probability that there will be 8 or more women in our sample of 50 engineers. Since we've already calculated our sample proportion in step 2, we will write our event of interest as the probability that our sample proportion will be greater or equal to 0.16. In step 5, we're going to convert our sample proportion to a z-value. So again, we've got our sample proportion minus our population proportion divided by our standard error. and the standard error uses our population proportion to determine this. So plugging in our numbers, we have 0.16 as our sample proportion and 0.10 as our population proportion. And we'll plug in our population proportion, again, in our standard error formula, along with our sample size of 50. Using your calculator, in our numerator, this is our sampling error. And we're going to take 0.16 minus 0.1. That'll give us 0.06. And for our standard error, when I plug in my values here and square root the entire thing, you should get 0.04242. When we divide our numerator by our denominator, we should get 1.41 as our z-value. Now we can use our appendix to determine the probability. So when we go to the appendix and you look up 1.41, you should get 0.4207. But recall, in our curve, we know that the appendix only tells us from the mean out to our z-value, but we're interested in greater than our z-value. So you'll subtract the area that is given to us in our Appendix D, the 0.4207, from 0.5. And that'll give us the area that we are interested in that is greater than 1.41, or the probability that our sample proportion will be greater than 0.16 at 0.07930. In other words, there's nearly a 0.08 or 8% chance that the sample would contain 8 or more women. Let's do part B. Same story. 10% of U.S. engineers are women. In part B, how likely is it that a sample of 200 engineers will contain fewer than 5 women in these positions? Again, step 1 is we want to find our population proportion. Recall that's given to us in our story at 10%. So I'll write this as a decimal, 0.10. In step 2, we want to calculate the sample proportion. So we're going to look at our pieces in part B. In this case, we have our sample of 200 engineers. So we'll put that in where our n is. And we're interested in knowing the chance that it will contain fewer than 5 women. So our x is still our attribute of being a woman. And here, the number specifically is 5. So when we take 5 divided by 200, our sample proportion is 0.025. Do not round. In step 3, we want to define the event of interest according to our question B. In this case, we want to know the probability that our sample proportion is fewer than 0.025. In step 5, we'll convert our sample proportion into a z-value by plugging our sample proportion and population proportions, as well as the sample size, into the formula. So we'll plug in 0.025 minus 0.1 and plug in our population proportion in our standard error formula, as well as our sample proportion of 200. Thus, our sampling error in our numerator is negative 0.075. Recall that you can have a negative sampling error. When we calculate the standard error in our denominator, you get 0.0212. When we divide our sampling error by our standard error, we get negative 3.54. And why it matters that our sampling error is negative, which then affects our z-value. The negative z-value tells us that we're on the left side of the curve. So here we'll go ahead and use Appendix D to determine the probability. When you look at the Appendix D, you'll notice that it does not go past 3, because Appendix D does not show values as high as plus or minus 3.54. Recall that when we're looking at the standard deviation in our normal distribution, it goes out 1 standard deviation, 2 standard deviations, or 3 standard deviations, and should contain virtually all of our values. Anything greater than 3 standard deviations from the mean, either positive or negative, either right side or left side of the curve, is considered an outlier. These are very extreme values. So this implies that the probability that our z is less than or equal to negative 3.54 is pretty much 0 chance, or it's a very, very small number. And if you use Excel to find the exact value, it's going to be like 0.000000 out several decimal places to a very minuscule number. And again, if you want to imagine it as a curve, if I draw my curve and I'm out to negative 3.54, that line of my curve is very close to the x-axis because it's very, very small chance of happening. In other words, what we're saying is that there's nearly a 0 chance that our sample of 200 engineers would contain fewer than 5 women. So let me know if you have any questions or concerns.